Take a look at this problem right here. If you're looking at this and going, what the heck is going on? Then watch this video. Today, we're gonna be talking about continuity at a point. And by the end of this video, you should be able to solve this problem. Everyone, today we're gonna be talking about continuity. Yesterday, we talked about discontinuity. Now today, we're gonna be talking about continuity. Discontinuity was things that are gaps or something that split up our graph. Continuity is just the complete opposite. If it wasn't split up, it's connected, right? Some sort of way of kind of showing connectedness. One way we describe continuity that's kind of unrigorous but gets the idea down is if you can draw the graph without ever picking up your pencil, then it's continuous. That's how we kind of describe continuity without any rigor or any proof-based stuff. So we're going to be talking about continuity at a single point today. And then next time, we will talk about continuity on intervals, right? We can figure out that this whole line right here is continuous, but today we're only going to be looking at a singular point and trying to show that a single point on a graph is continuous. And then later we'll go to the other one. So what is continuity? Now I can say that continuity is when you don't pick up your pencil. But the exact way to say it is that it is when the limit, the two-sided limit as x approaches a of f of x equals the actual function value defined. So for example, we had discontinuities that look like this. This is a removable discontinuity where there was a hole and the point that there was actually defined at was different. The limit is this value right here. The actual point that it's defined was down here. Because the limit did not equal what the actual value was defined, that was a discontinuity that we talked about. Another one that we talked about was the jump discontinuity. It looked something like this, where halfway through the graph, we would jump up to something else. The problem with this one is that the limit, the two-sided limit is not even defined, right? We need the two-sided limit to be defined and equal to the function value for this to work. But because the one-sided limit on the left goes down to this value and the other-sided limit goes to this value, that means our two-sided limit can't be defined, and that way it won't ever equal any of our function values. And our last one that this diagram is going to show is the infinite discontinuity that we talked about. This one has a problem because the function isn't defined anywhere. The limit is going to infinity, but if we're talking about the extended reals, but the function isn't defined anywhere because the values just keep going up to infinity. There's not even a value that we can conclude at this x equals a point. But if we can make sure that those three things don't happen and we can find that the limit equals the same thing as the function value, then what we have here is a continuous point. All right, let's take a look at an example. This example is asking us to see if x squared plus 1 is continuous at x equals 3. And if this is our definition right here, we need to find the two-sided limit, and we need to find where the function is defined at x equals 3. And then we have to show that they're either equal or not equal. If we have any problems getting there, then it was discontinuous at x equals 3. So the limit as x goes to 3 from the positive side, because remember, we have to do both sides separate, and that will inform us on our two-sided limit of x squared plus 1. Well, that's going to equal 3 squared plus 1. That equals 10. And if we do it from the other side, the negative side, the left side of x squared plus 1, that's going to give us 3 squared plus 1. That's going to equal 10 as well. So our two-sided limit is also going to equal 10 because the one-sided limits both equal 10. So we can go ahead and write that down right here. X squared plus 1, that equaled 10 because the left-handed and right-handed limits both equaled 10. All right, and it's very easy to see that we can also plug in 3 into our function, which is also equal to 3 squared plus 1. This is going to give us 10. So our function value at x equals 3 is the same as the limit approaching x equals 3. So what this means is that x squared plus 1 is continuous at 3. All right, here's another example. Is x cubed minus x continuous at x equals 0? That's the question we're trying to solve right now. We want to know if the point is continuous. And the way that we do that is we need to show that the limit as x approaches 0 of this function is the same thing as 0 cubed minus 0, or the function value at 0. And this one's pretty easy. This is equal to 0, but we need to check this here. So let's do our left-handed and right-handed limit. All right, so now we have the left and right-handed limit in place right here, and you can see that both values end up going to 0. And when the left and right-handed limit meet, that means that our answer for the two-sided limit is also 0. Given that the limit is the same as the function value in this case, it is continuous at the point x equals 0. All right, welcome back to the problem. Do you guys know how to solve continuity at a point now? Can you show me if this is continuous at x equals 2? If you can, you understood the lesson. If not, you're going to have to go back and check again. The limit as x goes to 2 of the square root of x must equal our function value at x equals 2. So in this case, by plugging in 2 into our function, the limit must equal square root of 2. So we have to check the left and right-handed limits. The limit as x goes to 2 from the negative side, square root of x. We can use direct substitution. That equals square root of 2. And you can check it from the positive side. It is also going to equal square root of 2. So both sides equal square root of 2. That means our two-sided limit right here also equals square root of 2. And when the limit equals the function value at our point x equals 2, yes, this is continuous. And that is continuity at a point.